Welcome everybody to my presentation about experimental and numerical investigations in limit strain and ductile fracture. My name is Florian Fehringer. I'm a PhD student from the University of Stuttgart in Germany. I want to start with a short motivation for limit strains. There is a permanent risk of environmental caused incidents which might exceed design limits of components. And if you think of earthquakes, they might exceed the design limits multiple times in a short period of time. For example, that's a pipe summer from the 2011 earthquake in Japan. And stress-based criteria are not able to evaluate scenarios like that. So maybe for the evaluation of safety margins, a limit strain concept might be an option. So, talking about limit strains, there are a lot of influence parameters on limit strain. I pointed out 5 down here. For example, non-proportional loading of the material. Very important is the stress triaxiality on limit strains, the component size, or multiple loading situations. So the content of my presentation, I already showed a short motivation. Then I will show a possible strain-based safety assessment concept. I will talk about the damage mechanics simulations we need for the strain concept, and then I will show some experimental numerical investigations we did so far. I will show a fracture strain curve we derived from that experimental investigations, and I will show in an outlook the future planned experimental and numerical work. So our strain-based safety assessment concept is based on such a limit strain curve, which gives us a tolerable plastic strain, accumulated equivalent plastic strain, as a function of different parameters like the stress triaxiality, loading angle, component size, load histories, and so on. And of course, our limit strain curve must contain a safety factor. So how do we get those limit strain curves? We do a kind of material characterization, so we do some specimen tests, which on one hand directly influence our limit strain curve, and more important, are needed for our finite element simulations. We do 2 kinds of simulations, some simple elastic plastic simulations for things like the plastic strain or the stress triaxiality and so on, and some damage mechanics simulations which we need for the crack initiation location and the crack initiation time. So when we have our limit strain curve and we want to evaluate a component, we take that component and an assumed load case and just have to do an elastic plastic simulation. We take our plastic strain and our influence parameters out of the elastic plastic simulation and look into our limit strain curve, and if we are below the limit strain curve, the load case in the component should be safe. If we are above, then it's a not safe loading case. So the damage mechanics simulations, we are using the local damage mechanics model of Rousselier. The Rousselier model is for ductile failure under tensional load, under tensile load. And ductile failure under tensile load can be described by 3 different stages. So first we have void initiation for the material we are looking at. Happens as soon as our equivalent stress reaches the yield strength. After void initiation, we have a growth of the voids, which is described by Rousselier model. Rousselier model is strongly dependent on the hydrostatic stress. And at the end, when the void volume reaches the critical value, we have a coalescence of the voids, which finally leads to the fracture of the specimen. So the problem is, Rousselier model is not capable of describing shear dominated failures, so small stress triaxialities, and multiple loading situations because it's missing a kinematic hardening claim. So in our work we have to do at least two extensions. First, to describe shear dominated failure, we are looking for a coupled approach by introducing a new damage parameter describing the shear damage and adding a term describing the shear behavior, which will depend on the loading angle parameter. For kinematic hardening, we will define a backstress tensor which describes the kinematic hardening effects and which will influence our stress tensor we use for our Grosselier model. So the experimental and numerical investigations we did so far. First of all, what's the material we're using? We're using a ferritic steel. It's a ferritic steel representative for German nuclear power plants. And we take all our samples out from a pipe, which has an outer diameter of 800 millimeter and a wall thickness of 47 millimeter. First of all, to describe the homogeneity of the material, we did 15 aneaxial tension tests. We described the specimens around the circumference, and we took specimens in longitudinal and circumferential direction. And as you can see, we have a quite good homogeneity of the material, which is kind of important for our concept. We also used those tension test results to derive our true stress strain curve, which we also need for the Grosselier model simulation. Second step is the numerical calibration of the Grosselier parameters. So we used notch-round tensile bars with in total 3 different notch radii. We have a 10 millimeter notch radius, a 4 millimeter notch radius, and a 2 millimeter notch radius. And as you can see with the Grosselier parameters down here, we are very well able to describe not only the elastic plastic behavior of the material, but also the failure or the crack initiation and also the failure behavior. You can see on the left, you can see the load displacement behavior. For elongation of the specimen, on the right-hand side we have the load necking for the reduction of diameter in the notch. So after the numerical calibration, we did some validation of our Grosselier parameters. We used 2 different CT25 specimens, CT5 specimens with and without side grooves. And as you can see in the middle, with the parameters we obtained from the notch-round bars, we were quite capable to describe the load crack opening displacement behavior for both the side-grooved and the non-side-grooved specimen. What we also can do is simulate the crack front of the specimen. You can see the crack front at the end of experiment for the experimental side and the numerical side, and they fit also quite well. And the same for the strain distribution on the surface of the not side-grooved CT25 specimen. So all in all, we have good results regarding the load COD behavior, the crack front, and the strain distribution. As I already said at the beginning, the loading path might have an influence on limit strain, so we did first tests on the influence of loading paths with a 2-step test where we changed the stress triaxility during the test. We first had some simple smooth round bars which we pre-strained to a total strain of 4, respectively 8%. Afterwards, we took those specimens back to the workshop, added the notch to it, and so increased the stress triaxility. And what you can see on the left is the load displacement behavior during the preload, and on the right we have the load displacement behavior for the notched specimen. Into 2 different notch radii. Notch radius 2 millimeter and notch radius 10 millimeter. And as you can see, with an increasing preload, so we have no preload, 4% preload and 8% preload, we get an increasing maximum load, and which is more important, we have a reduction in the global deformation capability of the material. So the question now is the Grosselier model capable to describe such a situation with changing triaxility, changing geometry? So same as for the experimental procedure, we did a 2-step simulation. So we first pre-strained a smooth bar, and after 4, respectively 8% total strain, with an element depth option, we changed the geometry to a notch geometry and continued with the simulation. And on the right diagram you can see, as one example, the 2 mm notch radius, 4% pre-strained specimen in blue, and you can see also load displacement behavior and the crack initiation time could be described very well by the OCE model. Okay, so all the experiments I showed before we used to derive a fracture strain curve. Why is it a fracture strain curve and not a limit strain curve? Because it only contains stress triaxility and much more importantly, it doesn't contain any safety factors. So the fracture strain curve shows us the accumulated efficient equivalent plastic strain and crack initiation as a function of the stress triaxility. And as you can see, for high stress triaxility values, we can fit the curve with a decreasing deformation capability with an increasing stress triaxility. We also took our results from the preloaded specimen to look into the influence of changing stress triaxility and limit strain. And you can see here the specimen with a 10 mm notch radius, which have a smaller stress triaxility, and there's hardly no influence on the preload regarding the fracture strain. For the 2 mm notch radius specimen, we have with an increasing preload, with an increasing pre-strain, we have a reduction in the tolerable plastic strain and a slightly increase in the stress triaxility. So, as the project is right at its beginning, I'll give you a short overview on what we are planning to do to extend our limit strain concept. First of all, we're going to apply it to a second material, not an ferritic steel, but an austenitic steel instead. And we are also looking into size effects. We'll do a set of experiments with notch round bars in total different sizes, but all the same stress triaxility, as you can see in this picture here. Brussellier model already predicts a slight reduction in limit strain regarding the size, but we have to prove it with experiments first to be sure. We are also looking into the influence of mixed mode loading via compact tension shear specimen. Those are specimens like that. They consist of a regular CT15 specimen, and by the specific clamping we can generate a mode 1 loading for loading angles of 0 degree, and a mode 2 loading if we turn it 90 degrees and have a loading like that. We have a pure mode 2 loading, and for 30 and 60 degrees, of course, we have a kind of mixed mode in between mode 1 and mode 2. For the loading path influences, in addition to the pre-strained notch bars, we have tension torsion and torsion tension specimen, which we will load also in 2 steps, not simultaneously. And we have notched hollow cylinders under pressure and tensional load, which we will apply pressure and afterwards the tensional load to see the influence on the changing stress triaxility. And the CTS specimens, the compact tension shear specimens I showed in the slide before, we will also use in 2 steps tests, changing the loading angle at least once during the experiment. For multiple loading situations, we do some cyclic testing with approximately 10 cycles till failure. And we will use smooth and notched specimen, and we will apply a constant amplitude loading and an increasing amplitude loading for both type of specimen. So the conclusion, at first I showed a possible strain-based safety assessment concept, and then I showed the capability of the Brussellier model, which is able to describe material behavior for high stress triaxilities and changing stress triaxilities, but which needs some extensions to describe shear dominated failure and kinematic hardening behavior. A fracture strain curve we could derive from the experimental results in the regime of high stress triaxilities. And on the last 2 slides, I showed our intended experimental investigations to enhance our limit strain curves by the influences like material stress, transitivity, small value size effects, loading paths, and multiple loading situations. So that's the end of my presentation. Thank you very much.